welcome to this session where we're going to be taking a look at verification and SystemVerilog for beginners. So my name is Dave Long. Okay. So I've been working at Doulos for over 20 years now, and one of the main things that we do at Doulos is teach engineers about other scripting languages and verification. So it's one of my goals. Now, what I'm going to be presenting in this next hour is not like a condensed version of one week's worth of training. The idea is really to give particularly people who are beginners who haven't got a background in verification and understand as to what verification really means, and to give you an introduction to the SystemVerilog framework. Again, I'm not going to go through the syntax. I'm simply going to point out some of the main features, because to learn it, you really need to spend time and play with it. So this is really just to give you a heads up as to what to expect in terms of verification and in terms of SystemVerilog. Okay, it's not a substitute for actually sitting down and learning it yourself. Okay, so I hope you're still happy to go through that. So let's get a move on, because we've got lunch afterwards. We've got lots of slides to go through. Is the technology going to work? I suppose we can. No. Oh, yeah, just needed to go to sleep. Right, okay, so what we're going to be covering in this section, first off, taking a look at background to verification, so different verification approaches, how we construct basic test benches, some of the terminology like functional coverage, and also formal verification. So what's the difference between that and simulation? Okay, so really just a 10,000-foot view. It's not going to be looking at the details. And then with the second part, we're going to take a look at the basic structure of SystemVerilog. So verification, what does it really mean? Well, it's all about finding out whether we've really built what was intended. Okay, so if we've got a device, is it going to behave as the specification said? Okay, we need that specification, and when we do the verification, we may have our particular version of the design. So it could be an RTL model that we're going to synthesize. It could be netlist. It could be something that's more abstract. Okay, but we want to check, does it meet the requirements of the specification? So we could have a starting point of a specification. It could be some existing model that we're going to use as a reference. And we need to have some environment for doing that verification. So our verification environment typically would be something like a test bench. There's different ways of approaching verification. Okay, so if we break this down, then we can split that into different approaches. So simulation is the most popular approach for verification. Okay, so that's traditionally what people do. The other branch that's increasingly becoming interesting is formal verification. Okay, so we'll take a look at some of the features of formal verification towards the end of this part. And if you would come to the session this afternoon, we'll take a more detailed look at what formal verification is all about. And there's other techniques that we may use as well, such as acceleration and emulation, to improve the performance of our verification. We can break down formal verification into two different categories. So we've got property checking, where we're going to be looking at properties that we have actually written, so extracted from the original specification. So is it doing what it's supposed to? Or we've got equivalence checking. Is it doing the same thing as something that we know already works? It's even possible to combine formal approaches with simulation. So one of the problems with formal verification is it can be very challenging if you've got designs that are very complex to be able to comprehensively test them. So dynamic formal can effectively run a simulation to get you into an interesting state, and then use that as the starting point for your formal verification. Some other terms you might come across, or with simulation, we can talk about transaction level modeling. And transaction level modeling is a way of abstracting away unnecessary communication details, so you can still get the right functionality, but things that would otherwise hold up the simulation, we can just forget about. For simulation, constrained random is a technique that's used to help you to automate the test vectors that you're going to apply. So the stimulus that's going to be the inputs to your test benches, if we can generate them automatically, then we can generate a lot more and a bit higher quality test vectors. So constrained random is a technique for that, which we'll look at. Assertions, that's testing against properties. So if we describe the behavior as a formal property, we can have an assert statement, and we can use that in simulation. So when you get to an interesting set of values, we can check it's correct. We can use it with formal verification. Okay, so that's a powerful technique. And coverage, again, can be used for both formal and simulation approaches. So we're measuring what has actually happened when we've done our verification. So have we tested what we thought we were going to test? And constrained random stimulus is one of the features that we would expect to see in a so-called intelligent test bench. Now, if we're going to write some kind of a verification environment, we need to think about the language we're going to use. And there's more than one to choose from. So traditionally, it was just down to languages like VHDL or Verilog. Okay, so you go back 20 years or so ago when I first joined Doulos, we were running VHDL and Verilog courses. That was our main business. Then those languages work, but in terms of verification, there are some things that they lack. So some features which could help with the verification, which are more software-like, are not part of those languages. So other languages have been developed. PSL, another IEEE language, the property specification language, provides a mechanism for writing those formal properties. SystemVerilog is probably the most popular verification language in the world today. It's a strict superset of the Verilog language, so it grew out of Verilog plus some other language elements, and since 2009, Verilog officially has just been a subset of SystemVerilog. Okay, so the Verilog standard is not being maintained as such. There are other approaches. So the E language was, again, sort of promoted as being the way forward 20 years ago. So it's an aspect-oriented language, which allows you to extend features in your test bench dynamically. So it's sort of sometimes described as being like object orientation on steroids, because you can do lots of other things with it. That requires lots of specialist knowledge. It's not used that much these days. Okay, there are one or two companies that have stuck with E because they like the power of it, but it requires a lot of discipline to use properly and to understand. There's also quite a lot of interest in the C++ community with creating test benches in C++. So we could use the standard C++ language, or more likely System C. So again, System C has been around for over 20 years. It's just a C++ class library with a set of rules. But if you're creating virtual prototypes where you want to create a model where you're going to be running software on a mock-up of the actual hardware, then System C is really the leading technology in that field at the moment. Okay, so we could write test benches in System C. And again, you might have heard of SystemVerilog UVM. Well, there's even a System C implementation of UVM if you really want to go down that route. And of course, there's also other languages that people use to help with test benches. So scripting languages like Tcl, Perl, Python. More recently, people have even looked at using Python to actually generate test benches. So we're going to focus on SystemVerilog a little bit later on, because as I said, that's the most common. Now, in terms of approaches to verification, there's different ends of the spectrum. So, on one hand, we've got ad hoc approaches. At the other end of the spectrum, we can have a really formal, disciplined approach. And an ad hoc approach might just be to be writing with programmable logic just to program it, see if it works. Okay, so going back 20 years, we sometimes had a hard time persuading engineers that they even needed to write test benches, because they took the approach as, well, if it doesn't work, I'll just reprogram it. Problem is that as designs become more complex, that really isn't an option. You can't easily test really complex behavior on the physical device. You don't have enough probing points. You don't have the visibility of what's really happening internally, which you can do with an HDL model. So getting a bit more disciplined, we have a VHDL or SystemVerilog test bench, and we can run simulation. We can enhance that with other languages or techniques such as C++, SQL, Python, Perl, and so on. So some people like to incorporate models written in C or C++ within their VHDL or SystemVerilog simulations. So both those languages have a mechanism that allows you to easily connect your VHDL or your SystemVerilog world with C. Okay, so you could take advantage of that if you've got models maybe coming from something like MATLAB that you want to integrate as a reference model in your test bench. With constrained random verification, then things get a lot more complicated, because the test bench itself has to have the ability to deal with the knock-on effects of having random inputs. We can have transaction level modeling, say abstracting away features like we do in System C for more complex environments. For really complex things, we can speed things up by using hardware. So maybe putting some of the test bench into actual FPGAs or racks of logic gates, which is what acceleration and emulation does. Maybe running FPGA prototypes to see whether that is going to work. And perhaps most formal of all, we've got formal verification, which requires a completely different approach to writing traditional test benches. With these more complex approaches, typically you have an environment where you've got a verification team and a design team, because it becomes too much for individual designers to also write all the test benches as well. And so it's common in a lot of companies to separate those two. So designers might write some simple test benches like we have up here, but for more complex verification, there'll be a separate verification team. So what is verification actually doing? Where is it applied? So if we take a typical design, starting point might be a specification. We're going to write some code, maybe in VHDL or whatever language you prefer, synthesize it, we get our RTL code. Sorry, we write our RTL code in that language. We then synthesize that, we get a gate level description. If it's a chip, then that will go on to the back-end process until we get to the master layers. And verification is required at each of those steps. It won't necessarily be the same approaches, but we still have to verify it. So how do we verify the RTL code actually matches the specification? How do we check that the synthesized RTL matches the gates? Because there could be bugs in tools or bugs in libraries. There could be differences between the way languages are interpreted at simulation and synthesis. And similarly, we could have bugs or mistakes in the layout or the bit stream we're going to program it. So each step has to be verified. And to do that verification, unless we're doing a completely ad hoc approach, we need some kind of plan. And that's something that new verification engineers often neglect, the requirement to actually sit down and plan things. You don't just dive in and start writing some tests, looking at waveforms and deciding whether it works or not. You need a more formalized approach. So what are we going to verify? Okay, so we need to look at the requirements based on the original specification. How are we going to verify it? Okay, so what approaches do we use? How are we going to generate the stimulus to identify whether our design is working correctly, to find bugs? How do we measure success? Okay, so that's can be quite challenging. It's not just a question of applying some waveforms to the input, looking at the outputs and saying, yes, that just works fine. Okay, how many different scenarios are you testing? Okay, so we need to know what do we mean by success. So that's the job of the verification plan, is to actually write down somewhere a document that can be examined by someone who's doing an audit to check to see how you've actually done the verification. Have you actually been thorough enough? Are there any things you've missed? So in particular, if there's something in the specification, it needs to be tested against. Okay, so you can't just, if it's in the specification and you don't test it, then either the specification is wrong or ambiguous, or you haven't done a proper job of testing. How are you going to test each feature? So there may be some features which you can test together. There may be other features that require totally different test benches or totally different approaches. So the verification plan can identify those differences at an early stage to make sure that you include everything that you need to. What sort of testing do we do? Are we going to do directed testing? So directed testing is where you sit down and you decide a sequence of inputs that are going to be applied and what the expected outputs are going to be. Okay, so that's great for simple designs, maybe even like a state machine. You could say, okay, I know how it should behave. I'm going to write some inputs to run through the state transition diagram. If it's more complex, maybe we want to use constrained random testing instead. And constrained random testing allows stimulus to be generated automatically. Therefore, we can generate a lot more stimulus and run many more tests in time available. Okay, so if we've got constrained random stimulus, that means we don't know in advance what the inputs are going to be for the device that you're testing. So if you don't know what the inputs are going to be, how do you know if it's working? So we need to have also some way of checking built into the test bench so it can identify whether your tests are passing or failing. Okay, so that's important. So verification plans vary enormously. They could be something like a spreadsheet, it could be something written on a whiteboard. But in general, every verification plan will have a starting point, which we're looking at the points in the specification, and it will identify how each of those points are going to be tested so that someone can tick off to find out, is it working or not? So we could have an example here where we've got an output pin that needs to reflect a particular register bit. So we could have a structured test where we're going to write a sequence of values to the inputs and check to see if we have the expected behavior. Okay, that's perfectly valid. We could run that test. Somebody else could read the verification plan, rerun that test, and confirm that it's working as expected. Okay, because remember that designs are typically worked on by more than one person. So the person that writes the original tests may not end up being the one that runs the tests on some future variation of the chip. Or we've got another bit here related to a checksum, or maybe we're going to identify whether that's working correctly by generating some random data and looking at the functional coverage. So how many times do we see certain things happening? Okay, so different approaches, but they're still in the verification plan. Okay. Now, there's various tools that might be used in addition to just something like a simulator. One of the issues of some languages is that they are perhaps easier to make mistakes in than others. So a language like VHDL has strong checking that's done by the compiler. So in one respect, a language like VHDL is great for writing RTL code because if it compiles, there's a good chance it's going to work. Verilog doesn't take that approach at all, and neither does SystemVerilog. So they are much more flexible, which can make the code easier to write, but you have a problem where you can write code that compiles, which is functionally incorrect. Okay, so that takes experience to understand and to do it correctly. So there are linting tools available which can effectively analyze your code in order and tell you if you've done something stupid. Okay, and those are very common in the Verilog and SystemVerilog world, because the compiler doesn't do that checking for you. Okay, and It could be linting tools, which is just looking for particular constructs, so effectively just doing searching of regular expressions and finding out what you've done. Or it could be a formal analysis tool that's doing static analysis, sort of symbolic analysis of the code to find out are there things that could be potential bugs. Okay, but if you can run those before doing simulation, then you can speed up the verification because you're not wasting time running tests that are going to fail. So simulation is all about executing a model of the system. Okay, and sometimes people sort of look at simulation and say, well, it's a model, it's not really the same thing, therefore it's not valid. So it's important to make sure that your model is an accurate reflection of what you're going to be building. Now, if you're writing RTL code, then that RTL code is going to be synthesized. The RTL code already contains descriptions of where all the registers are going to be, what happens on each clock edge. So that's a pretty good model. It's pretty accurate in terms of if your VHDL or Verilog model does something on a particular clock edge, then you can be sure the hardware will do so as well. Okay, but depends how much accuracy you really need. And the problem's always been, when you're writing a simulation model, the more accurate it is, the longer it takes. Okay, and the approach that's taken to modeling has varied over the years. So maybe back in the 1970s, the best you could do would be to run a splice simulation of transistors. But that takes forever. If you want to speed things up, maybe you can replace the transistor models with voltage-controlled switches. Okay, so that simplifies the work of the simulator. It's still, for a digital circuit, you can still get good accuracy, but that's still slow. So languages like VHDL and Verilog actually model the behavior of the code that you write by looking at when particular processes are going to be executed, when signals are changing, and so on. If you want to have more speed up, again, abstracting away unnecessary details by things like transactional level modeling. So there's this trade-off between accuracy and simulational speed, which you can't get away from. Okay, so it's about picking the best representation in terms of accuracy that you need and trading that off against the speed. So if you're writing a model that is simply going to be running, let's say, some IP core corresponding to an ARM processor, and you've got a bit of logic around the edge of that, and you want to run software on it, then you don't need to have a gate level model of that microprocessor to run simulation. And so you can rely on the fact that maybe your ARM core or your RISC core is going to behave correctly. So you want a more abstract model that's going to behave the same as far as the software is concerned, and all you really care is about the interfaces around it in terms of timing accuracy. Okay, so that sort of model will give you the benefits of running fast enough, but still give you accuracy where it's needed. Okay, so simulation can be used across all those different types of applications. Okay, now when we simulate a digital system, then we've got typically our RTL code, register transfer level code, in case you're familiar with that. Could be written VHDL, Verilog, SystemVerilog, whatever. We want to run some tests, so we need to generate some test vectors. So the term test vectors is just the term that's used for the inputs to what you're trying to simulate. And then we get some outputs, so we'll call those the output vectors. Okay, so simulation just runs through all of the input vectors, generates the outputs, and then we can check them. Okay, so if we're writing these vectors by hand for a particular sequence of inputs, that's known as the directed test. If we're generating them automatically, then that's where constrained variable comes in. So the results we get depend on the nature of the model and the simulation. Okay, so it's an approximation, but that approximation would normally be good enough. The actual semantics depend on the language that you're using and the simulator you're using. Okay, so stimulus is going to determine the quality of the test. So ideally, we want to have stimulus which is going to reveal bugs, but we're not going to waste time simulating unnecessary features or repeating tests that we've already done that are not going to show us anything new. So the results that we get depend on the design and the stimulus. We can't do much about the design, but as verification engineers, we can look at the stimulus. Okay. We need to check to see whether it's working correctly. So I'll talk more about that in a minute. But say the general problem is that simulators are never fast enough because you always want to get the results immediately, and particularly with complex designs or accurate simulations, for example, involving things like mixed signal designs, then that can take a very long time to actually do. To do the test, we need to have some environment to insert our design into. So we've got our design under test, that's what our DUT stands for. We can create a test bench, so using a language like VHDL or SystemVerilog, for example. And here, for example, we've got our stimulus. Okay, so in this case, we've got some Verilog or SystemVerilog code for the stimulus. That stimulus could be, say, written by the designer, it could be read in from a file maybe, or it could be generated automatically. And for a basic test bench, we might just look at waveforms. That's a really poor way of doing the test. Okay, because we'd like to be able to automate it. If we can automate it, we can speed up the time it takes. Because remember, we haven't got enough verification engineers to do all this testing. Okay, so the test bench sends the stimulus. Ideally, we'd like it to be self-checking. Okay, so even if we're doing directed tests, it still helps if the test bench itself can tell us whether it worked correctly or not. It's the test bench, one way of thinking about it is provides a test environment. So if you're testing something on the board, then you would have a test bench that you would inject signals with tools like oscilloscopes, logic analyzers, and so on in order to do that. So the test bench in simulation serves the same purpose. It provides the inputs and checks the outputs. It could be written in the same language as the final testing, or it could be written in another language. Okay. And one thing to remember is that when you're writing the test bench, you typically don't need to worry about synthesizing the test bench. So you can use the full range of features in the language that you're using. So things like types that are not synthesizable, so like dynamic arrays, for example, in SystemVerilog, you can't synthesize them, but they may be useful for storing results in a test bench. Now, creating the code for a test bench can take a great deal of time and effort. So we want to be able to simplify things, to reuse as much as possible from one project to the next project. And that means we need some sort of standard structure for the test bench. So we've got a stimulus generator, it's going to be generating a stimulus. We've got our design under test, and we've added a component that will automatically check the input against the outputs. Okay, so in our checker, we've got some mechanism to calculate the expected results by looking at the same inputs to the device under test, generating the expected, and then comparing them. Now, on the picture, it looks simple, but this may be incredibly complicated. So there could be some kind of reference model in here, could be some kind of algorithm. So that itself could take as much effort, if not more effort, to create the natural design under test. So it's not unusual for test benches in terms of lines of code to be many times bigger than the design that you're testing. Okay, so that's why it's important to be able to reuse as much as possible. Now, in terms of generating the inputs, then looking for the sorts of things that cause problems is a skill that you learn, but in particular, areas that represent the extremes of values are often candidates for causing problems. So you often hear the term boundary expression and corner case. So the boundary is simply going to be, for example, our 2/8-bit values, the boundaries represent on this graph, the combinations of the maximum and minimum inputs. When we've got both a combination of two maxes or two mins or whatever, we've got the corners. And again, corners are often where things go wrong. So you often hear the term corner case to represent the verification engineer has found some combination of inputs that cause a problem. So the term corner case is often referred to those as well. But this is where it's originally come from. So we need to think about where we're going to sort of write our test vectors. And if we're generating test vectors by hand,
these boundary conditions and corner cases are important ones to include. If we're using formal verification, then formal verification will cover everything, so that's not so much of an issue. But if we don't have to generate effects by hand, if we could generate automatically, then that would allow us to automatically cover all those corner cases and much more without having to waste time writing all the tests by hand. So that's where constrained random comes in, and that's, say, the most popular technique in the SystemVerilog world. Okay, so we can't test everything because it's just too complicated. So constrained random tests are designed to pick a good selection of inputs so that we can get a representative cross-selection of possible inputs that are going to cause problems. Generating random numbers is easy. The problem is random numbers by themselves are not terribly useful because we could have lots of invalid combinations of inputs. So in order to make it useful, we need to have constraints. So languages like SystemVerilog have a constraint solver built into the simulator. So you can actually specify conditions to determine which random numbers are going to be generated, or the rules for generating random numbers, so that the random numbers, for example, always represent realistic inputs. Okay, so you've got meaningful values. And it may use a combination. So for example, here we could have, let's say, a CPU. So we want to generate a stream of opcodes. So they need to be valid opcodes, but maybe things like the data and address fields are going to be randomly picked. Okay, so that's been shown to be good at picking up unexpected errors. So with that approach, we can start to automate things. So our test bench has now got some more intelligence in it. So we're generating our inputs randomly. With random inputs, we're going to get random outputs. So we've added our automatic checker. But there's still one thing missing. And that is, if we're generating the inputs randomly, how do we know whether we've met the requirements in our verification plan? So we need functional coverage. And functional coverage is going to keep track of what particular values or states within our design have done. And then when it's seen the conditions it's expecting, it'll tick that off. So the idea is we can, at the end of the simulations, see have we achieved all of our goals. If we haven't, then maybe we need to run the simulation for a bit longer. Maybe we need to modify the constraints to home in on the bits that are missing. Okay, so that's what Testbench automation is all about. That's the approach that is used, for example, in UVM. Acceleration is a way of speeding things up. Now, one way of speeding things up may be to simply use a more powerful computer. Okay, but there's limits as to how far you can go with that. Okay, so if you've already got the biggest, sort of most powerful PC on your desk, then there's not much you can do to improve on that. Maybe you can distribute simulation between several computers. Okay, so EDA vendors have simulators that will run across multiple cores, so they can take advantage of some parallelism. Or maybe we need a really powerful server. So we have one server in the company, and everybody uses that for running their simulations. Or maybe that's not enough. We need to go into the cloud and hire a whole bunch of compute farms off an Amazon Web Service. Okay, so those can speed things up, but that can get very expensive. Okay, so if you have a look at the cost of some of these Amazon servers, they're not cheap. Maybe we can speed things up by removing unnecessary details. Okay, so if it's modeled at a low level, of transistors, for example, it's going to be slow. So ideally, we want to only model the design and the test bench at the level that we need. And if we don't need low-level details, model things more abstractly. Okay, so rather than, for example, modeling data transfers by looking at every bit of a bus, and every bit represents an event that has to be processed by the simulator, perhaps we could generate something like a transaction to represent a complete bus read or write cycle, or even a burst on the bus, rather than just doing it at a low level. So that's what transaction level modeling is about. So in transaction level modeling, things like it works best with things like bus activity, because we can replace, say, a complete operation on a bus with a function call. So rather than having to represent separate events for each bit of each wire on that bus, on every clock cycle, we can have a single event corresponding to a read or write function. Okay, we're losing low-level details, but maybe that doesn't always matter. Okay, so System C does exactly that with transaction level modeling. UVM has borrowed those ideas into the transaction interfaces that are used between UVM components and the UVM environment. I mentioned coverage. Coverage we could take as just being, have we covered everything in specification? But coverage has specific meaning in the context of verification. So we could talk about code coverage. So have we executed every line of code? Or functional coverage, have we actually seen the states that we were looking for? Okay, so they're done differently. So here's an example. So in this case, we've got a block of VHDL code and apply some tests. As it runs through, the simulator can count how many times each of these lines gets executed. Okay, now, what does that tell you? Well, it certainly doesn't tell you if the design is working correctly. But it can be useful for a number of reasons. Firstly, if we get lines here that never get executed, there could be two reasons for that. It might be that we just haven't generated the correct input stimulus, in which case we could address that by just running a simulation for longer, or, more worryingly, it could indicate a design bug that we need to fix. Okay, so code coverage is useful, but it doesn't actually tell us anything about whether the design is correct. So normally with coverage, we talk about functional coverage. And languages like SystemVerilog include specific syntax to make it easy to create cover groups. So a cover group is going to record information about how values are changing in your test bench. And in this case, we're triggering it on a clock. So every time we get a positive clock edge, we're going to update the values in here. So each cover point will be something that gets recorded. So typically it could be the name of a variable, or it could be an expression. Okay, so that gives us information about what's really happening in our test bench. We can even break down cover points into individual bins if we want to have more fine-grained knowledge. So we run our simulation, and at the end of the simulation, we've discovered that we've got a value missing here. Now, that's important because it means we haven't actually tested what happens in that case. So again, that could indicate that we just haven't got good enough test vectors, or it could mean that there is some state that can never happen. So we need, either way, we need to examine the cause for that. But the fact that we've got a gap in our coverage bin tells us that we need to investigate it. And that's what we need to know. If we get to the end and we've got 100% coverage, then it means that we've met all the goals that we set out to. Again, it doesn't tell you that your design is working correctly. It simply tells you that you've seen everything that you said you wanted to test. Now, that may not be sufficient because you may have not written enough cover groups. Okay, so you still need to have all this information in the verification plan so that somebody else can check it. So in terms of code coverage versus functional coverage, if we get high for both, that's great, we've met our goals. If we've got high code coverage but low functional coverage, then it means that our tests are executing the code correctly, but we're not seeing all the states that we need, so we need to look at the stimulus. If we've got high functional coverage and low code coverage, then that sounds suspicious. So maybe our cover groups are not really testing what we expect. Maybe we've got cover bins which are just too broad. So we're getting hits which are not actually telling us anything useful. And if we've got low for both functional and code coverage, then we've got a lot more work to do. Okay, so in terms of coverage, then if we look at all the states that we could get in a design, with directed tests, we can only ever cover a tiny proportion of the possible states. Okay, so that's the main objection to doing directed tests. We can say, yes, it works under these conditions, but there's many more conditions that we haven't tested. Random tests, we can, because the tests are being generated and run automatically, then we can get much greater coverage. But it's still going to be a tiny subset of the total. With formal verification, we can comprehensively say every possible state has been addressed, because the formal verification tools use different techniques. They use symbolic analysis to work out are properties going to actually be true or false. So we can get 100% pass or fail answer. The issue is that it's hard to do that. So if we've got a simple design, let's say a finite state machine with 10 different states, that's not too bad to verify. If we've got 100 different states, it becomes a nightmare. The tools simply can't cope with that complexity. The state space is too deep. So in those cases, we can maybe get a partial solution by having what's known as bounded formal. So we can set boundaries around parts of the design and then do comprehensive analysis on those parts and then join the whole things up. So different techniques are used, and maybe we need to use a combination of techniques rather than just one, which is, say, the topic of the next seminar this afternoon. So formal verification, what we're talking about here is formal methods. There's a variety of techniques that we saw earlier. We've got things like just comparing two models or doing property checking. But in both cases, they don't need fingerprints. Okay, so we can check that everything works as expected, but it only really works for relatively straightforward examples. Like state machines are ideal, a memory would be really bad. So that's why we don't just use formal verification and throwaway simulation. Equivalence checking is basically checking that two versions of the design are functionally the same. So it will effectively extract the Boolean logic that represents two different versions and compare them. Property checking, we write properties, and those properties are proven or disproven. Okay, so formal verification, again, can be used at each different step, but would likely be different. So with a specification, we'll probably write properties, and then the formal verification would do property checking to check those. Between RTL and gate level, or gate level and layout, we would do equivalence checking. Okay, so those will be different tools. Equivalence checking, so just checking that the two are the same. With property checking, then we write properties. So assertions in a suitable assertion language. So let's just finish this section off by looking at assertions. So with assertions, we can have something like an assert statement, and what we give it is a condition that's either true or false. Okay, so it could be a simple logical expression, output 1 is greater than output 2, or it could be a temporal expression. So for example, here checking when input 1 rises, check that the output 1 is greater than output 2 clock cycles later. Okay, so that requires a more complex syntax. Okay, so let's move on to quickly looking at SystemVerilog. And again, here just to introduce the main features of the language rather than giving you a comprehensive guide. So SystemVerilog was designed right from the start to be a hardware design and verification language. So it wasn't restricted to just the likes of what Verilog can do, but it was a superset of Verilog. It's gone through various revisions. We can also talk about different subsets. So the RTL part of the language, there's an assertion part of the language, and the testbench part would be things like the class-based environment that's used by UVM. Okay, so here's the same information, but dividing it differently. So the RTL includes lots of features that come from C. So things like C data types like enums, structs, type defs. So if you know C, you'll recognize all of those, because they're exactly the same. Some improvements to write synthesizable code. So again, we're not really talking interested in those in this section, in this conference, but things like better always blocks for flip-flops or combination logic and so on. Packages just like VHDL, and interfaces to manage things like buses. There's a separate part of the language which is purely used for assertions. Okay, so some people write SystemVerilog assertions to verify VHDL designs. Okay, that works. And there's testbench features, things like classes, constrained random stimulus, functional coverage, and so on. Okay, and there's also, say, the interface to C. Okay, so parts of SystemVerilog are simply improvements on Verilog. Okay, so fairly things that were missing from, say, VHDL, or things that could be added from C. The classes and the other test bench verification features are completely new compared to Verilog. And then there's some stuff in the middle which we're not going to talk about. So there's historical baggage that's been picked up. Okay, so the class-based verification bits are the bits of interest. Just out of interest, SystemVerilog has also simplified the way that Verilog represents states. So Verilog doesn't really have a concept of a type. You have wires and variables, and you assign x's and ones and so on to them. In SystemVerilog, there is a logic type to represent that. So logic is for state. It can be signed if you want to represent 2's complement numbers, but there's also a 2-state type if you want to improve, slim down the test benches. So if you don't need to worry about x's and z's, then you can just use bits. And then there is these other types here which are 2-state, which are designed to map onto C. So those are particularly useful if you want to interface to C programs. Okay, here's an example of a type that's come from C. So the struct type in C is visible or available in SystemVerilog. In C, it's normally preferable to use type defs. We can do the same thing in SystemVerilog as well. Okay, so this defines a type where we can have members of different types within that and refer to them by name. So just like a record in VHDL. Okay, so here's some examples, creating an instance and then using the dot operator to access its members. And there's also notation for being able to assign all of the elements in one go. That's known as an assignment pattern. So similarities from C there. Interfaces don't really have an equivalent in other languages, but it's a convenient way of grouping together a bunch of signals, such as a bus. And with the interface, for example, here we've got an interface representing an AMBER APB bus. So the signal's on that bus. And with the interface, where it's neat is that we can connect the interface to a module via an interface port. So we can effectively replace a number of separate connections with a single connection. So it just streamlines the connectivity at the high level. Now, in terms of assertions, there's various ways of writing those. We could just use the assert statement inside a process. Okay, so that's not what we'd use with property checking. So that's just something that's true or false, and if it's false, then we can get it to stop the simulation. Okay, so similar to the assert statement in VHDL. Where it's different is if we say assert property. So assert property is known as a concurrent assertion. So it runs, typically we need to specify a clock that's going to run on, and then the condition is something that we can either test during simulation time or can be proven by formal verification. Usually, when we're writing assert properties, we have a more complex expression where we have an antecedent or precondition and an implication operator and a consequent or condition. Okay, so that basically says that if we see certain things on the inputs, that implies we should see something happen on the outputs. And that's what we normally want with property checking. Here's some further examples. So we put labels on our asserts to make them easier to identify, and we also then get the label repeated when they get a message from them. It's also possible to cover a property. So this is not the same as functional coverage. Cover property simply counts how many times that property passes. So it gives you similar information to functional coverage without using cover groups. And it can also be used with formal verification. So we can find out whether properties have been correctly covered when we're running formal verification, even though we don't have any stimulus. It just says, is this state reachable? That's what it tells you in formal verification. And assume is used in formal verification to provide constraints on the inputs to blocks. Again, it takes the syntax, same syntax as assert property. Assume property in a simulation works the same way as assert property. So it will run it in a simulation, and if it passes, it typically doesn't do anything. If it fails, it will write out a message or stop the simulation. So generally with properties, we want to describe what happens over time. So temporal expressions means the properties here consume time. So here's an very simple example. So we would read this as saying that on every positive clock edge, we're going to check that if we have a sequence where A is true on one clock cycle and B is true one clock cycle later, that implies that D should also be true and E should be true one clock cycle after that. Okay, so that's something that could be tested at simulation time by looking at the actual values of A, B, C, and A, B, D, and E, or it can be proven by a formal verification tool. So are there any combinations of inputs or states that would cause this to break? That's what the formal tools can tell you. Now, we often have things like resets and other conditions that we need to take into account. So if we're looking at the behavior over multiple clock cycles, then typically we want to put a disable in. So in this case, disable if, for example, we've got a reset happening. Otherwise, you'll get false negatives. So you get failures which are not real failures because it's just been interrupted because of reset. So the disable prevents that. So that's the basic syntax there. Okay, now, if we're writing a complex verification environment in SystemVerilog, we're going to be using classes. UVM is based on classes. So the rest of this section, we'll just have a look at how classes are used in SystemVerilog. And I'll go through them fairly quickly, but I'll give you a pointer at the end as to where you can try these out for yourself if you've got access to a browser with EDA Playground. So here we have a class. So a class is a keyword with end class, and inside our class, just like a struct, we can have data members. But in addition, we can have member functions. So just like classes in C++, except in SystemVerilog, the class syntax is actually based on Java rather than C++. So if you come across Java and class, then you should recognize some similarities. Okay, so we've put our class in a package. So bus transaction is a data type. Okay, we don't need a type def in there. So to use that, we need to create an object. And the way you create an object is we create, first of all, some variables of the class type, and then we need to call new. Okay, so T1 and T2 are just two variables that can point to a bus transaction object. No bus transaction object exists until we call new. So new creates this new object. Okay, so we've got a bus transaction, we've got some default values in its fields. We can now start using it. But until you call new, if you try accessing T1 or T2, you'll get an error. Having created a new transaction, T1.data is going to pick up this value or assign that value there. Now, one thing you do have to watch out for is that because T1 and T2 are effectively just handles to a bus transaction, they behave like pointers in C. So if we assign T1 to T2, we're not effectively creating a new object. We've still only got one object because we've only called new once. But now T1 and T2 are both pointing to the same object. Okay, so that's the thing that often catches people out when they learn about classes in SystemVerilog. But we can use T2 now in exactly the same way as T1. We can update the data, so that's overwritten this value. If we call T1.print, because T1 and T2 are pointed to the same object, then what we get back is the value that T2 is written. Okay, so that's the way that classes work. Now, when we create a new object, typically we want to have some control over how it gets initialized. So we can add a constructor into our class, which is a special member function for doing initialization. Okay, so rather than just calling new and some default values being there, we can actually add a function new into our class. And the job of that is to provide the initial value. So every time we call new, that function now gets called. Okay, so that's now going to create our new object and initialize it. We can also create a function new, and just like other functions in Verilog and SystemVerilog, add arguments. So that gives us greater control over how objects are going to be initialized. Okay, so we can only have one constructor though. SystemVerilog doesn't support function overloading. So we can only have one function new inside the class. So if we specify the function new takes an argument, if we call new with no argument, that's now going to give you a compiler error. Okay, so we have to pass that in. We can work around it because we could provide a default value for the argument. So that would allow both of those to work, but that's just an aside. Okay, so what else can we put in the class? Well, one of the most powerful features is that we can add random members into a class. So if you put a rand keyword in front of this data member, that will automatically get randomized every time we call the randomize function. Okay, so here's an example. We've got our bus transaction handle TR. We're creating a new object. After creating a new object, we're calling a randomize function. So that's going to randomize the values of those fields. So direction, address, and data will get random values. Okay, so that's what that bit's doing. Randomize actually returns a true or false. So here we're just throwing that away. And then we're calling the print function to print it out. So we go around this loop 3 times. When we call new again, that creates a new object. Okay, so the old object is no longer being accessed. So it automatically gets garbage collected. Okay, so it gets cleaned up automatically. Okay, and we're now pointing to, TR is now pointing to a new object, which we're randomizing again. And again, we can do the same again with the third object. Okay, so creating objects, randomizing objects, cleaning up when they're finished works very easy in SystemVerilog. Now we need a test bench. So I'm going to speed things up a bit because we've still got a few slides to get through. So with our test bench, we actually want to provide a complete environment. Okay, so we've got a stimulus generator, we've got a checker, and we're going to write that. And ideally, we'd like to make this a class because classes are much more flexible. So our device under test, we're going to put into a module providing the low-level signals for driving it and clocks and so on. But everything else we want to put into a class, and then we can put those classes into packages and reuse them. Okay, now, test bench components, if we're using classes, that's different from the transactions. Okay, so in terms of lifetime, modules, instances, and so on get created once at elaboration time, but objects get created at runtime. So we've got 2 different types of object. So objects which are the verification environment, again, we only want to get one copy of that gets created at time 0, whereas transactions are going to be created as we run through the simulation. Okay, so they're both created dynamically, but they have different characteristics. So, here's our top level. So we still need to have a module to insert our class into, because something has to call new. Okay, so we've got our environment. We're going to create that into our test bench module, and we're assuming that our environment has a run function, which is going to write values to the device under test. Okay, so here we've got a hierarchical path name, and we've got a test harness module that contains the device under test. Now that will work, but I said we want to have reusability, and the problem is we can't put a hierarchical name like that into a package. Okay, so that's not a good solution. So SystemVerilog provides a workaround which allows you to create what's known as a virtual interface. And the virtual interface is like a pointer to an interface. And that means it's just a number So we can put that into a class. But here we're passing it in through the constructor. And then when we create our top level, we can specify that this environment hook points to the actual instance of the interface. Then this interface is going to connect up to the signals in the test harness. Okay, so in our test harness, we've got device under test, and we've got our interface, and then we're wiring them up, will be shown there. Okay, so that's fine because interfaces and modules and so on are static. So here's the bit where we're connecting things up. So at the top level, we've got our environment class that takes the virtual interface as a constructor argument. We've got our TB top that instantiates the environment and passes in a path to the actual interface, which is sitting inside the test box. Okay, so that completes it. Okay, so if you're attending this afternoon session, we'll revisit this when we have a look at how that works. Okay, so that's our basic structure. Now, in terms of randomization is great for giving us multiple values, but we don't want it to be completely random, we want constraints. So we can add constraints into the class as well. So we can have data members which are constraints, which specify the restrictions on what the random values can be. Now, yeah, just finish. So if these are, if this is representing a device with some read-only memory and some write-only memory, or read-write memory, then we don't want to write to the read-only memory. So we could add a constraint that prevents writes to anything that's less than 7FF. That in itself isn't terribly useful. What we want is an implication constraint, because the implication constraint effectively says when the address is less than 7FF, then the direction must be read. Okay, so that's the way that we normally write constraints. So we have a sort of, we could also write it as an if-else constraint. Okay, now that constraint we could put in the original bus transaction, but that's going to limit the reusability for that bus transaction in other test benches. So a better solution is to create a derived bus transaction class. So that's what we're doing here. We're creating a memmap transaction class that extends the original bus transaction. And all we need to add in here is the constraint and a constructor. Okay, so that means if we look at a sort of UML type diagram, we're taking our original transaction, we're creating a new derived class that adds a constraint and, in this case, a control knob for controlling that constraint. And what we end up with is everything we've inherited plus the things we just added. And the really neat thing is that this new class can be used anywhere where the original bus transaction class would have worked. Okay, so we can add extra features into classes by extending them without breaking existing code. Okay. And finally, just functional coverage. We can put functional coverage into classes as well, except in this case, we're calling a sample function. Okay, now, final slide here. In order to learn SystemVerilog, you really need to write some code and play with it. And a couple of people said, how can I do that when I don't have access to any tools? Well, EDA Playground is a website that's provided by Doulos, and it does give you access to those tools. So you can write your code on here. There's lots of examples already existing that you can play with if you're learning SystemVerilog. You can pick which tools you want. So all of the major EDA vendors are supported in terms of their simulation tools. There's also a couple of synthesis tools, and you can run this live. So that's the URL to type in. Again, you've got it in the notes as well, and copy the slides. Okay, so that's the end of this section. So sorry for overrunning slightly. This afternoon, if you're able to attend, then we'll continue by taking a look at UVM and also an overview of formal verification. Okay, so thanks for doing. Oh, one other quick thing. If you want to know more, go and or more information, go and chat to Hannah on our stand, and she's got some golden reference guides to give away to anyone that asks them. So she's got a limited number, but she doesn't want to take any home. So, if you want one of those, then I suggest you go and talk to her after lunch.